The use of steel is considered an indicator of a country's level of industrialization, and the steel industry is also referred to as the mother of industry. This highlights its importance. The steel industry is a fundamental sector for national construction and a key industry that must be prioritized for economic development. It has a significant impact on related industries, with downstream sectors including metal manufacturing, machinery, automotive, shipbuilding, transportation equipment, electrical equipment, civil engineering, construction, and even the defense industry. The industry plays a crucial role in driving the development of related downstream industries, improving industrial structure, and promoting sustained economic growth. To stimulate more robust economic development domestically, the government has constructed a China steel mill as part of 10 major construction projects. The civil engineering of the first phase of the first stage of the construction of China Steel Mill was managed by the Ret-Ser Engineering Agency. There were 21 construction units, divided into 87 construction projects, which commenced in September 1974 and were all completed on schedule by November 1977. Each project met international standards in construction quality, fully demonstrating RSEA's high construction performance. The China Steel Mill is located in the 4th Linhai Industrial Park in Saigang District, Kaohsiung. The area, originally a reclaimed land, spans 480 hectares and was traversed by the old Yanchuigang River. It was covered with fish ponds, sugarcane fields, and muddy marshes. The soil was soft with low bearing capacity, necessitating geological improvement before it could be used as the site for the massive mill buildings. During the initial construction phase of China Steel Mill, managed by the RSEA, the most crucial task was the installation of Raymond piles beneath each essential foundation. These piles were designed to support the future steel mill's weight on soft soil layers. Raymond piles are a type of modern foundation pile, made by connecting 7 to 8 sections of pile shell, each featuring spiral grooves on the exterior for tighter soil integration. When driven into the ground, these piles can reach depths of up to 102 meters, with the shortest being 72 meters. After installation, each pile's surface bearing capacity can sustain between 75 to 135 tons. The installation of Raymond piles utilized a special steam hammer to drive the pile shell into the ground, segment by segment, with each hit delivering 40,000 pounds per foot of force. Driving pile casings several dozen meters long into the ground with millimeter precision according to the design location is indeed a highly specialized construction technique. In the foundation work for China Steel Mill, most of the Raymond piles were vertical, but a portion of them were batter piles at angles up to 15 degrees, requiring even finer construction skills. The 84-chi inclined piles at the coking plant are capable of bearing larger lateral loads. After the installation of the Raymond pile shell, the next step involves lowering a prefabricated steel reinforcement cage into the casing, followed by pouring concrete. Only then is the preliminary work of a Raymond pile considered complete. During the first phase of the first stage of construction for China Steel Mill, the RSEA employees worked tirelessly through all weather conditions, day and night, to install over 22,500 Raymond piles. This feat was accomplished in just 1 year and 4 months. This achievement was not only unprecedented in domestic construction history, but also a rare accomplishment in the annals of global engineering. In the foundational engineering of the first phase of construction, besides driving Raymond piles, a variety of precast concrete piles, steel pipe piles, steel sheet piles, and sand piles were also installed beneath other less critical foundations within the mill area. If these foundation piles were connected end to end, their total length would exceed 1 million meters, enough to circle Taiwan 1.5 times. This underscores the immense effort and toil contributed by the RSEA's employees and highlights the formidable nature of the construction task. Another important construction task in the foundational engineering of the first phase of China Steel Mill was the ground reinforcement of the raw material storage area. To prepare the 24-hectare storage site to bear the heavy load of iron ore, the soil needed to be improved. The initial phase involved soil replacement and compaction, followed by the installation of drainage sand piles and compacted sand piles. A total of 365,317 meters of piles were driven, enabling the ground to support a load of 37.5 tons per square meter. To ensure quality, the area was further pre-pressed with sand piles and equipped with various testing instruments to monitor the effectiveness of the reinforcement. Test results confirmed that the foundation reinforcement work had achieved its expected outcome. Dock construction was a preliminary part of the first phase of the mill's construction. The finished product dock, measuring 152.8 meters in length, served both as an export terminal for finished goods and as a material transportation dock during the steel mill's construction. The raw material dock, extending 536.92 meters in length with a depth of 12.5 meters, was designed for unloading raw material ores and is among the deepest docks in the world. During the construction of the dock surface and crane foundations, what's particularly notable is that the RSEA employed a large vibratory pile hammer for the first time in the country. This equipment was used to install over 200 sets of double H-shaped steel sheet piles. Each of these steel sheet piles weighs 22 tons and is 30 meters long, equivalent to the height of a 10-story building. After driving these double H-shaped steel sheet piles into the ground, a solid underwater steel wall was formed between the sea and land. This wall serves as the most robust foundation pile for the dock's quay walls. To complement the construction of the two aforementioned docks, the RSEA also deployed several large dredging vessels to carry out dredging operations along the waterfront of both docks. The mud and sand excavated during this process were then used for land reclamation as part of the mill's foundation. While foundation piling and dock construction were underway, earthworks for the foundations of each plant also commenced independently. From foundational excavation, backfilling, land reclamation, and leveling to the installation of the plant framework, the construction proceeded from below ground to the surface, and then from the surface upwards. The construction units of the RSEA demonstrated high construction performance in the first phase, thereby ensuring that the subsequent construction of the upper structures of the plant buildings could proceed as planned and smoothly. In the upper structure engineering of the first phase of the plant construction, the steel plate mill occupies the largest area and has the widest spread. The rust water pits and channels within this plant are the largest and deepest underground structures among all the China Steel Mill's buildings. The construction of the pit foundation structures and pipeline installation was carried out 12 meters below sea level, presenting significant challenges. Despite facing numerous difficulties, the tasks were successfully completed thanks to the fearless spirit and determined effort of the RSEA's employees. The construction characteristic of the mill area is that there is a significant variation in foundation heights. Not only are the structures complex, but the number of bolts and embedded items is also exceptionally high, totaling more than 35 tons. There are over 13,000 foundation bolts alone, requiring extremely precise measurements during installation, with deviations not exceeding 3 centimeters in any direction, up, down, left, or right. Additionally, there is a vast quantity of concrete required for pouring. The steel plate mill is one of the key facilities among all of China Steel Mill's plants, and its construction is complex and challenging. Completing all foundational work took 2 years and 3 months, making it the mill that required the most manpower of all the buildings. The RSEA has set many impressive construction records at the coke oven plant. Underneath the coke ovens, 3 layers of 1 centimeter thick galvanized iron plates are used, with graphite powder sprinkled between them. This allows for slight movement during earthquakes, reducing damage. The coke oven features 4 barrier walls at both ends of the platform, each standing 19.935 meters high, to protect the brick-built furnace. Along the base of these walls are the coke oven's flue gas channels, comprising 6 arched culverts leading to the chimney for waste gas emission. The chimney of the coke oven plant is nearly 125 meters high, with foundations reaching 3 meters underground. The structure's steel reinforcement is very dense, and a significant amount of concrete was poured. The above-ground structure utilized a patented construction method from West Germany's AHI company, featuring a vertical variable diameter steel slipform. A hydraulic system was used for automatic form climbing, with position measurements taken after every 25 centimeters increase. A technical team of 27 people operated in continuous shifts, allowing for an average daily form elevation of about 7 meters. The RSEA set a new domestic construction record with the chimney work, completing a chimney over 100 meters tall in just 25 working days. Additionally, the 100-meter-tall chimney for the sintering plant was constructed in just 16 days. The construction of the coal storage building next to the chimney was particularly challenging due to the presence of 16 large funnels inside, which required the formwork assembly and steel reinforcement to be angled according to the design, making the construction exceedingly difficult. Fortunately, through precise calculations by the engineers, a 3-layer wooden column structure was erected at the bottom of the coal chute. Then, concrete was poured in 4 stages at a height of 29 meters. As a result, this building, aside from the chimney, became the tallest structure in the entire project, successfully completed to satisfaction. The main body of the coke oven platform is constructed entirely of refractory bricks, comprising a total of 39 coke ovens. Each oven has a capacity of 37 cubic meters, capable of accommodating 20 tons of coke per batch. This makes it one of the most crucial coke-making facilities in the entire steel mill. The construction of the iron-making plant was the project with the tightest schedule. After commencing on July 20, 1975, the RSEA urgently deployed a large number of personnel and machinery to expedite the work while closely monitoring construction quality control. Within the complex foundation structure of this project, special attention was given to the embedding of preformed holes and the pouring of large quantities of concrete, all of which were completed under strict quality control measures. The heart of the steel mill is the steelmaking plant. The embedded components in the plant's foundations are also highly complex, with approximately 1,500 bolts and 1,000 preformed holes. To ensure the smooth installation of the plant frame and machinery, precise measurements are required for fixing before pouring concrete. The iron components of the raw material storage tank funnels need to be welded in the processing plant first, then lifted and fixed on site. Due to the difficulty in controlling the slope of the troughs, precise skills are required during construction. The first stage of the plant's structural construction also includes several major structural plants. The most prominent feature of the slab and bloom steel mill project is its foundation, which consists of mass concrete, with numerous preformed holes distributed on top. Originally, the plan was to use the caisson construction method to sink these double cylindrical structures to the intended depth. However, after considering suggestions, it was decided to switch to conventional construction methods. Among these structures, the slab steel mill features numerous special bolt anchoring holes designed by German engineers. The area of the billet steel mill is over 17,000 square meters. The notable aspect of the project is that the roof foundation of the mill's structure is integrated with the machinery foundation. The entire civil engineering project was completed in August 1976. The wire and bar steel mill is primarily comprised of 2 gigantic steel frame mills. There are as many as 3,508 buried bolts for the roof trusses and machinery bases, along with 772 concrete column foundations, making the project considerably massive in scale. The raw material conveying system is located between the raw material storage yard and the coking and iron-making plant. The project includes construction items such as the coal blending bin, conveyor towers, and bridge foundations. The byproduct plant features a variety of on-site engineering tasks and produces various byproducts during the coking process. The water supply system plant, the largest of its kind domestically, consists of a complete set of water supply and water treatment equipment. Construction projects include the intricate installation of water pipelines, pumping stations, 8 water treatment systems, industrial reservoirs, sedimentation tanks, and aeration tanks, covering an area of approximately 5 hectares. The pipeline transportation system at the China Steel Mill is built on a foundation of 1,487 precast concrete piles with a diameter of 45 centimeters. The railway system project within the mill area involves laying 20 kilometers of cast-in-place railway tracks, connecting various plants and surrounding the main steelmaking area, facilitating the transportation of raw materials, products, and molten iron within the plant. The construction at the China Steel Mill ranges from simple to complex projects, each large and distinct. Construction of some subsidiary plants includes the oxygen plant, burnt lime plant, and power plant. The foundation civil engineering of the plants was also completed on schedule thanks to the efforts of the construction personnel, in perfect coordination with the installation operations of the various stages. In the first phase of construction at the China Steel Mill, over 420,000 cubic meters of concrete were poured successively. At its peak, it set a record of pouring 3,750 cubic meters of concrete per day. In November 1975, more than 43,000 cubic meters of concrete were poured in a single month, setting an unprecedented record in the domestic engineering industry. RSEA undertook the foundation civil engineering for the first phase of construction at China Steel Mill. Thanks to the exemplary teamwork and unwavering dedication of all RSEA employees, the construction tasks were successfully completed on schedule despite numerous challenges. Premier Chang of the Executive Yuan also visited the mill area multiple times, where he listened to reports. He expressed satisfaction with the continuous introduction of new construction technologies during the construction process, which has led to innovative advancements in domestic engineering and construction techniques. The construction of the first phase of the plant was completed in 1966, followed immediately by production. Initially, it produced 1.5 million tons of crude steel annually. After the completion of the entire mill, the production capacity increased to over 6 million tons annually. By exporting its products, it earned a significant amount of foreign exchange, greatly benefiting the national economy. Meanwhile, RSEA also secured contracts for the construction of a cold-rolled steel plant in Indonesia and a paper mill in Pekanbaru. RSEA's quality management and work efficiency were praised by the French owners as the best in the world. Facing different competitive pressures and market dynamics, RSEA was able to adapt promptly, successfully completing tasks and gaining recognition overseas. After the completion of the first phase of construction at the steel mill, the government proceeded with the second and third stages of construction as part of the 12 and 14 construction projects. These complex phases were also entrusted to RSEA for execution. The quality of work and workload for these subsequent stages were even higher and more intense than the first phase. However, all skilled employees at RSEA demonstrated unparalleled morale, confidence, and perseverance, ultimately delivering outstanding results. As of today, China Steel Corporation's annual production volume ranks among the top 25 in the world. Being situated on the tiny island of Taiwan, which lacks natural resources for steelmaking, yet still managing to establish itself on a global scale, is truly commendable and deserving of admiration from people around the world. The achievements of the employees of RSEA and China Steel Corporation, who created this miracle 50 years ago, are truly admirable and shine brightly alongside the passage of time.